In this videotape, we're going to go over our work with exponents and radicals. Remember, this is just a review tape. We're just going to be going over examples. If you need help with these topics, we suggest you look at the videotape lessons. Okay, in the first example, we want to evaluate the following expression: 4 times 3 to the 0 minus 16 to the 3/4 power plus 27 to the minus 2/3. Okay, now the first thing we come to is 4 times 3 to the 0. 3 to the 0 is 1, and we get 4 times 1. Don't confuse 4 times 3 to the 0 with 12 to the 0, and think that the entire thing is 1. The 3 to the 0, that's 1, but 4 times 1 gives us 4. Okay, it's not 4 times 3 parentheses to the 0. That would be 12 to the 0. Okay, minus 16 to the 3/4. This is 16 to the 1/4 raised to the 3rd power plus 27 to the minus 2/3 can be rewritten as 1 over 27 to the 2/3 power. This gives us 4. Now, this is the 4th root of 16 cubed. 4th root of 16 cubed plus 1 over. Now, this would be writing it 1/3 to the 1/3 power squared. This would be the cube root of 27 squared. Okay, now you're not finished because 16, the 4th root of 16 can be evaluated further, and so can the cube root of 27. 27 happens to be a perfect cube. Okay, let's see what we get. 4 minus, now the 4th root of 16 is 2, because 2 times 2 times 2 times 2 is 16. The 4th root of 16 is 2, so 2 cubed, plus 1 over, the cube root of 27 is 3. This is 3 squared. So let's see what we have. We have 4 minus 8 plus 1/9, or, just put this a little higher, minus 4 plus 1/9. 4 minus 8 gave us minus 4. And then we can combine over denominator of 9. We have 1/9, and 4 can be rewritten as 36/9. So we have minus 4 plus 1/9 minus 36/9 plus 1/9 for a final answer of minus 35/9. Minus 4 plus 1/9 minus 36/9 plus 1/9 minus 35/9. In our next example, we have 2x to the minus 2, y to the 2/3, all raised to the 6th power over 10 by itself, and then in parentheses, x cubed y to the minus 3/2 raised to the minus 2 power. Now, don't let the fractional and negative exponents bother you here. Okay? Previously, you have done problems like x cubed y squared to the 4th over x to the 5th y cubed, say, when everything, all the powers were positive integers. And you took x cubed to the 4th power, y squared to the 4th power, x fifth to the 3rd power, and y to the 3rd power. And we want to do exactly the same thing here. Don't let the fractions and the negative numbers throw you. Approach it exactly the same way. That is, it'll be 2 to the 6th, x to the minus 2 to the 6th power, y to the 2/3 to the 6th power, over, don't forget 10 is not inside this parenthesis, so 10 is by itself, x cubed to the minus 2 power, and y to the minus 3/2 to the minus 2 power. Let's see what we have. 2 to the 6th. 2 times 2 times 2. Okay, that gives us 64. X to the minus 2 to the 6th power is x to the minus 12th power. You just multiply the powers. Y to the 2/3 power to the 6th power. You just 2/3 times 6. 3 goes into 6 twice. This gives you y to the 4th. 12/3, that's 4. Over 10. X cubed to the minus 2 power is x to the minus 6 power. And y to the minus 3/2 to the minus 2 power, you multiply minus 3/2 times minus 2, giving you plus 3 as the power. Okay, let's see what we have. We can now, moving this up here, break this up into, say, 3 smaller problems. 64 over 10 times, we have x to the minus 12 over x to the minus 6, and y to the 4 over y to the 3. Okay, 64 over 10. There are 2 is a factor in common in the numerator and the denominator. We can divide the numerator by 2, giving us 32, and the denominator by 2, giving us 5. So we have 32/5. X to the a over x to the b is x to the a minus b. That is minus 12 minus a minus 6. And here, y to the a over y to the b is y to the a minus b. When we divide, we're going to, the same base, we're going to subtract the powers. So 32/5, x to the minus 12 minus a minus 6 minus 12 plus 6, or minus 6 power, y to the 4 minus 3, or y to the first power, giving us, as a final answer, the x to the minus 6 can go downstairs for x to the 6, so we have 32y over 5x to the 6th. In the third example, we want to multiply and combine the following. X to the 2/3 times x to the 4/3 minus x to the minus 5/3. We're going to use our distributive law. A times, say, b plus c would be a times b plus a times c. And we're multiplying, say, x to the a times x to the b. We're going to add the powers. We're not going to let the fact that they're fractions or negative bother us. Okay? So we're going to get x to the 2/3 times x to the 4/3 minus x to the 2/3 times x to the minus 5/3. Just the distributive law. This times this minus this times that. And now when you multiply, and they have the same base here, we're going to add the exponents. X to the 2/3 times x to the 4/3 is x to the 2/3 plus 4/3, or 6/3. And here, x to the 2/3 times x to the minus 5/3 is x to the 2/3 minus 5/3, or minus 3/3. Giving us x squared minus x to the minus 1. And generally we like to leave our answers in terms of positive exponents, so we can say this is x squared minus 1 over x. And if you would further like to combine into a single fraction, we can combine over the LCD, which is x. We can rewrite x squared as x squared over 1 as x cubed over x, and then minus 1 over x, for a final answer of x cubed minus 1 over x. And here you were asked to multiply and combine the whole thing into one fraction. Otherwise, there would be nothing particularly wrong with x squared minus 1 over x. It was correct. If I just said get it in terms of positive exponents, x squared minus 1 over x is correct. If you want to combine into a single fraction, you can, the way we did over there. Okay, in our next example, we would like to simplify the square root of 9x to the 36 plus 16x to the 36. Okay, what you do not do is break this up to say the square root of 9x to the 36th and the square root of 16x to the 36th. Okay, the square root of a product is the product of the square roots, but the square root of a sum is not the sum of the square roots. This can't be done. Okay, so that's out. The proper way to do this is to combine the like terms. We have 9x to the 36th and 16x to the 36th. That gives us 25x to the 36th. And this we can, turns out it's a perfect square. We can take the square root. Now be careful here. It's the square root of 25, which is 5. The square root of x to the 36th, it's x to the 18th. It is not x to the 6th. You take the square root of the 25, but you have the power here. You don't take the square root of the power, okay? And it's simple enough to check that. If you multiply 5x to the 18th times 5x to the 18th, you get 25x to the 18 plus 18, 25x to the 36. So this is actually the square root, not 5x to the 6th. Okay, in our next example, we would like to simplify the following. The square root of 48 x to the 9th, y to the 16th. Okay, now this is not a perfect square. Okay, it's not like the square root of 25x to the 36, which we could simply eliminate the radical from altogether. This was a perfect square. What we can do in a problem like this is to put it in simplest radical form. That is, we try to break this problem up. Okay, we try to break it up into a perfect square portion and whatever's left over. Then we take the square root of the product, make it the product of the square roots. The part that's a perfect square, we can get rid of the radical, and then the radical remains, but involving a simpler expression. Okay, so we look for the largest perfect square factor, 48. Okay, 4 is a factor. It's a perfect square factor, but we can do a little bit better. 16 is a larger perfect square factor. Okay, 48 is 16 times 3. X to the 9th is not a perfect square. To be a perfect square for a variable, it has to be an even power, so we can write this as x to the 8th. And then you have another x to make x to the 9th. We check this multiplies to 48 x to the 9th, y to the 16th. We break it up into the square root of 16 x to the 8th, y to the 16th times the square root of 3x. This portion here is a perfect square. The square root of 16 is 4, and the square root of x to the 8th is x to the 4th. The square root of y to the 16th is y to the 8th. Remember, we take the square root of the constant here, but we have the powers because of the nature of working with exponents. 4x to the 4th, y to the 8th times the square root of 3x. And we have this now in simplest radical form. Okay, now what I'd like to do is a problem similar to the one we just did. I want to simplify. This time, however, the cube root of the same quantity, 48 x to the 9th, y to the 16th. Okay, in much the same way, we are going to break this up into a perfect cube portion and whatever's left over. This is the cube root. Okay, whereas before we were looking for perfect square factors of 48. 16 was the largest perfect square factor. We're now looking for a perfect cube factor. Factors over 1. Well, 2 cubed is 8. it is a factor. 3 cubed is 27. It is not. And 4 cubed, you're already too large. So the best we can do is 8. And that leaves us with a 6 to make 48. And x to the 9th. Well, x to the 9th was not a perfect square. Okay? We needed to be a perfect square, we needed an even power. Okay? To be a perfect cube, it has to be, the power has to be a multiple of 3, and x to the 9th, 9 is a multiple of 3. So we can write this as x to the 9th. Now also for this, we need, for a perfect cube, it should be a multiple of 3 to the power. So we'll write it as y to the 15th is the largest power. Okay, and containing 16, that's a multiple of 3. Then we'll need an extra y over here. So we have 48 x to the 9th, y to the 16th. So we break it up into the cube root of 8 x to the 9th, y to the 15th, times the cube root of 6y. Okay, the cube root of 6y, we can't do anything about. But this is a perfect cube. It's been set up in that manner. The cube root of 8 is 2. And now we take a third of these powers, because this is taking the cube root is like taking something to the 1/3 power. So it's x to the 9th to the 1/3 power. It's x cubed. And y to the 15th to the 1/3 power is y to the 5th. So we have a final answer here of 2x cubed y to the 5th, the cube root of 6y. Remember, say y to the 5th is the cube root of y to the 15th, because y to the 5th times y to the 5th times y to the 5th would be y to the 15th power. Okay. We now want to simplify the following problem. 5 times the square root of 12x to the 6th y to the 5th over xy minus 2x squared y, the square root of 27y. Before we can simplify, we'd like to combine the radicals, but of course you can only combine like radicals. Before we can make a decision, we have to put the radicals into simplest form. It's possible that when you put them in simplest form, you will have radicals involving that have the same quantity under the radical sign that we can combine. So let's see what we can do. The square root of 12x to the 6th y to the 5th by itself is not a perfect square, but we can break it up to a perfect square part and whatever's left over. The largest perfect square factor of 12 would be 4, leaving us with a 3 here. X to the 6th is a perfect square. It's an even power. Y to the 5th is not. Y to the 4th is, leaving us with just the y. So we have 5, the square root of 4x to the 6th y to the 4th times the square root of 3y over xy minus 2x squared y, the square root of 27y. The largest perfect square factor is 9, and that would leave us with 3y. Square root of 9 times the square root of 3y. So let's see what we have. 5 times, now this first radical in both cases is a perfect square. So we get the square root of 4 is 2, the square root of x to the 6th is x cubed, the square root of y to the 4th is y squared, the square root of 3y over xy minus 2x squared y. The square root of 9 is 3 times the square root of 3y. Okay, let's see what we have. X and y factor upstairs and downstairs. We can cancel them out. X goes into x cubed, leaves us with an x squared there, and the y will divide into the y squared and leave us with a y here. So we will have 5 times 2, 10, x squared y times the square root of 3y minus 2 times 3 is 6 x squared y times the square root of 3y. And we have like terms after all that can be combined. 10x squared y, the square root of 3y, minus 6x squared y, the square root of 3y, leaving us to have exactly the same variable portions here. So it's just 10 minus 6 for 4x squared y, the square root of 3y. In our next example, we want to multiply and simplify. 2 the square root of x minus the square root of 3 times 5 the square root of x plus 4 the square root of 3. We are multiplying two binomials, and we can therefore use the FOIL method. First, outer, inner, and last. First, we will have 2 the square root of x times 5 the square root of x. We generally write the constants first, so 2 times 5 square root of x times the square root of x. And then outer, 2 the square root of x and 4 the square root of 3, so 2 times 4 the square root of 3 times the square root of x. Inner, minus 5 times the square root of 3 times the square root of x. And last, minus the square root of 3 times plus 4 the square root of 3 minus 4 the square root of 3 times the square root of 3, giving us 2 times 5, that's 10. The square root of x times the square root of x, it squares out, just gives us x. Plus 2 times 4, that's 8. The square root of 3 times the square root of x is the square root of 3x. Minus here 5, the square root of 3x. Minus 4 times 3. The square root of 3 times the square root of 3, it squares out, it gives us 3. So we have 10x plus 8 the square root of 3x minus 5 the square root of 3x. Like terms, 8 minus 5 plus 3 the square root of 3x. And then minus 12. In problem number 9, also we want to multiply and simplify. We have here the square root of 2x minus 5, quantity squared, minus the square root of 2x minus 5, whole thing under the radical, squared. Some people might look at this very quickly and think that the answer is 0. Okay, but these are not the same thing. Here, only the 2x is under the radical. Here, the whole thing is under the radical. Okay, this means the square root of 2x minus 5 times itself. And this, of course, the whole thing, square root of 2x minus 5 times itself. This first one we can handle by FOIL. First, the square root of 2x times the square root of 2x, giving us just 2x. The outer is minus 5 the square root of 2x, and the inner minus 5 the square root of 2x, so we have minus 10 the square root of 2x. And then finally the last, minus 5 times minus 5, that's plus 25, minus, when we square this, we multiply this by itself, of course the square root is eliminated and we just get what's under the radical, 2x minus 5, but it has a minus sign in front. The minus, since minus 1 has to be distributed through the parentheses there. So we have 2x minus 10 the square root of 2x plus 25 minus 2x plus 5. Okay, the 2x's cancel. We get minus 10 the square root of 2x plus 25 plus 5 plus 30. Okay, in this problem we would like to rationalize the denominator. When we put something into simplest radical form, we assume that there are no radicals in the denominator. And if there are, we would like to get rid of them. Okay, so what we do in this problem is that we multiply numerator and denominator by the square root of 3. Okay, we have only one term in the denominator. Okay, the radical square root of 3 is involved. We multiply numerator and denominator to get an equivalent fraction. Remember, you are allowed to multiply top and bottom by the same non-zero quantity. In doing this, upstairs we get 5 the square root of 3. Downstairs, 2 the square root of 3 times the square root of 3. Don't cancel out the square root of 3s. This was the whole idea. We want to get no radical in the denominator. The square root of 3 times the square root of 3 is 3. 2 times 3 is 6. 5 the square root of 3 over 6. Okay, as our answer. Do not think that you can cancel the 3 into the 6. This is under the radical, and you can't mix what's under the radical with what's outside. Okay, now in the next problem, it's slightly different. We want to once again rationalize the denominator. But now, the denominator involves two terms. We have 7 over 3 minus the square root of 5. Okay, now simply multiplying top and bottom by the square root of 5, as we did before, will not work. Because when we have two terms here, as indicated by either an addition or subtraction, we must distribute, say, if we did do this, we have to distribute the square root of 5. You get 3 times the square root of 5 minus 5. In other words, you wouldn't get the radical here, but you would have it over here. If you did it again, you wouldn't get it here, but you'd have it here. So that's not the answer. What we do is we multiply by the conjugate. If you think of this as a minus b, then we multiply top and bottom by a plus b. Once again, we must multiply the top and the bottom by the same quantity. But it's been designed so that what we have up here is, what we have down here is a minus b times a plus b, and when you multiply it out, the square roots will drop out. We're going to do that by FOIL, and you'll see this. We have on top 7 times 3 plus the square root of 5, and on the bottom, using FOIL, first 3 times 3, outer is plus 3 the square root of 5, inner is minus 3 the square root of 5, and last is minus the square root of 5 times the square root of 5. So we have 7 times 3 plus the square root of 5 over. Now, of course, here, this 3 to the square root of 5 and minus 3 to the square root of 5 cancel out. We have 3 times 3, 9, minus the square root of 5 times the square root of 5 is 5. So we get 7 times 3 plus the square root of 5